First of all, thank you for the introduction. And also thank you all for actually staying here this time. It's a long day, and I think it's the last talk of today, right? So this is actually a collaborative work between our lab at Hopkins and the Siemens X-ray team from Germany. Just some quick acknowledgements for our labs and the funding support. So this work, we're going to focus on the bone marrow edema imaging. So the bone marrow edema is usually a result of some traumas and some chronic disease such as arthritis. Usually you can find this in the trabecular region with the increased water concentration and decreased fat. So basically you can detect it by MRI pretty easily. You can see this two examples on the right. Pretty strong edema signals on both of the trabecular regions. But still there are a lot of complaints about MRI for the cost and the speed of acquisitions. Usually not that ideal for edema imaging. But if you want to use a conventional CT as an alternative to image edema, the calcium background is too strong, so you cannot really see it. So recently, people have been started looking at using a dual energy conventional CT for bone marrow edema imaging. So the reason why is it allows us to do some calcium subtraction. So the way to do it is to run a three-material decomposition with fat, water, and calcium. And we show the edema using this virtual non-calcium imaging technique. This is those two colorful image on the very right side. It's basically a weighted sum of fat and water concentrations. So you can see this pretty strong edema signal shown as closer to water attenuation value shown on this image. In this work, we're actually going to focus more on the dedicated dual energy cone beam CT scanner for extremities. Or arms and legs, basically. And we all know that for cone beam CT, there are like a bunch of non-idealities, such as the detector artifacts, some scatter, and all of these are quite detrimental to the material decomposition for edema imaging, because the poor spectral separations between water and fat. And in this work, actually, we're going to focus on this scanner. This shown on the right side is the scanner designed by Siemens Healthineers, multi-term racks, two robotic arms. This cartoon here is actually when we configure this to a wrist imaging geometry with pretty high resolution. And actually, if you were in my SPIE talk earlier this year, we show a bunch of simulation studies that actually shows that it's feasible to run edema imaging with this dual energy cone beam CT geometry, given a certain level of artifact corrections. But here in this work, we're going to focus on all the real studies with physical phantoms and some cadaver studies at the end. And here to image dual energy, to actually apply dual energy, we use a fast dual kV switching protocols. So we assume that the switching speed is about 50 milliseconds. So at the end, it will give us about 0.5 degree of a spectral ray path mismatch between high energy and low energy. And this is I'm just showing you an overview of the framework that we use to process the dual energy data. So to start from this top left corner, both of these are raw data from the KV switching scanners, and we're gonna go through all of this process and reach this final non-calcium image. So it's a little bit overwhelming, but my point here is actually to show you we divided this into three compartments. So we start with the pre-correction step. We're going to do some detector artifact correction first, and then we run a sinogram interpolations because we have a mismatch ray. So we actually interpolate the high energy to match the low energy ray. So actually, I'm going to show you a couple of interesting results in the later slides to actually apply a very simple interpolation techniques, and that actually works pretty well. And then we're going to run this scatter correction block. And finally, we're going to input the scatter corrected projections into a three material algorithm to get the non-calcium image. So just a couple of remarks for each of this stage. So first of all, in the pre-correction stage, we have this, we want to do this lag and glare corrections. Basically two deconvolution process. The lag is a temporal deconvolution with the lag response function across all the executive frames. The glare is a two-dimensional deconvolution directly onto the projections. It's pretty standard. If you're interested, you can definitely check this publications. We use pretty similar method. And for the scatter estimation, so first we're going to combine this two energy channel and run a projection domain decompositions to get the two material images. The way we do it is pretty standardized. We do this PDD, we call it, we first do a pixel by pixel spectral calibration. So we have a spectrum for each of the pixel across the detectors. And then we generate a bunch of two-dimensional lookup tables and interpolate onto our measurement to get this water and bone intermediate image. So like up here. And then we're going to input these two material images into our Monte Carlo simulators to simulate scatters. And we use a relatively low number of photon plus some Gaussian smoothing to make this running pretty fast. So the last step is the material decomposition. Actually, we use this a two-stage decomposition process. It's originally proposed by Dr. Li Feng in Mayo about 10 years ago. And we actually modified it a little bit earlier this year in SPIE to actually allow it to directly generate the virtual non-calcium image. So the main idea is like this. So the first stage, it's pretty simple, straightforward, just a PDD step to give us the intermediate two material images. So here I'm using a polyethylene and aluminum as an example for the intermediate state. And then we're going to run an image domain change of basis. Basically, we're going to go from these two material bases to the final water, bone, fat, three material bases. And then we're going to recombine the water and fat to generate this virtual non-calcium image. But actually, if you think about the math from the two material image all the way to the end, is actually, if you do some matrix manipulations or linear process, you can boil things down into very simple equations down there. So you just input your polyethylene aluminum image into that equation and solve for this unknown Q is defined as the fat over the fat plus water is the fat fraction over the soft tissue, and that's directly related to the virtual non-calcium image at the end. But things getting pretty important. So there's one thing I want to point out is that there's actually you see this A and B. These are the four parameters or coefficients actually we need to calibrate in order to let this equation work. So the way we do it is pretty experimental. We do it calibrated directly from an intermediate PDD on the fly. So it's actually a step that is very similar to the image domain decomposition. We essentially crop it the region that we think is pure water, and then we use that as a water calibration, and then we do the same for the fat. Another thing is there's an R term on the very right side of this equation. So this is actually related to the bone coefficients. Normally, it's actually a knob that we can slide to adjust the value of R that we actually want to use to make the image look slightly better. But here we actually fix the constant R for all our studies. And this is just this is actually our axial view of our test bench in Hopkins. I guess some of you, if you sign up for the tour, you might be able to see it. So we configure this to just all powered by motion state. We configure this to the multi-tone Rex wrist geometry with about 1.55 magnification. The detector is just a Varex 4030 with no anti-scatter grid installed on there. And one thing I want to emphasize here is the air gap of this geometry is actually quite large, about 40 centimeters. So scatter is relatively not that significant. And you will see that actually a little bit later in the SPRs. And this is acquisition protocols, and this is just a video of the acquisition. So we actually use 60 and 120 kV for the low and high energies. We run a 200-degree short scan, and that's standard protocols for the Siemens Rex scanner. And again, we assume the 15 millisecond switching speed. So, I mean the switching intervals. So it end up with the average, switching average 0.5 degrees. So this is done by actually manually combine two separate scans of high energy and low energy and interlace them to create this kV switchings. For the phantom, we build our own phantom. We use the three different materials: the dipotassium phosphate to simulate the cortical bones, water for soft tissue and edema, and we use ethanol to simulate fat. And the phantom basically look like this bucket on the right side. And basically, the diameter is about 12 centimeters. It's actually a knee size, larger than the wrist. But and there are 5 inserts inside of it. So the first insert is called adipose. It's just purely fat, so we put only ethanol in there. And then the next 3 inserts are, we call it BME 80 to 100. So this number here actually represents the percentage of water or BME, the edema inside of the solutions. So the way we created is we fix this bones to be the constant values, and we increase this water and decrease the fat. So that will give us a gradient of edema in this phantom. And then there's a 5th insert called the BME 100 bone plus. You know, it's a little bit lengthy name, but basically we just dump a little more of a bone in there to create a little bit more beam hardening in this phantom. And this is just the initial FDK of it. Okay, so this is our plan for the bench study here. You can see that we actually acquired the data with 3 different collimations with 20 millimeter, 60 millimeter, and 50 millimeter. No, I mean 2 centimeter, 6 centimeter, and 15 centimeter axial collimations for the phantom. And in addition, we run a reproducibility test. Actually, I saw a bunch of presentations yesterday doing something similar. I think this is pretty cool, actually. So we placed the object, we shifted it actually about 25 millimeter at different locations in the field of view. So we end up with this 5 locations. So this yellow circle actually represents the center of this object. And we take a scan at each of these 5 positions for each collimations. For scatter simulations, we use a 10 to the 6 number of photons with variance reduction, and plus some pretty gentle Gaussian smoothing with the full width half max equal to about 10 millimeters. But in addition to this, we're not gonna just do a pure ideal scatter correction, but we want to test the sensitivity of this framework to the slightly different errors in the scatter. So we run 4 extra cases. So we have a 20% over and under estimation of scatter. So we created this by directly scaling our ideal scatter simulations. You can see the green lines and yellow lines in this plot here. We also run a mean scatter correction, or some of you call it constant scatter correction. So the way we created this here is we just blurred the ideal scatter with the very wide Gaussian kernels to make it look somewhat flat. It's not a constant though, but it's closer to a constant. And of course, we also run a no scatter correction case. And these are just 2 examples to show you like before and after scatter correction is the reduction of cupping in here, especially in the polyethylene image. So this is the intermediate image, the first stage of our 3 material decomposition process. And in addition, so if you remember, like I said earlier, that when we run the 3 material decomposition, we're calibrating this water and fat coefficients directly on the intermediate material images. So here, actually, because you're not going to prop the same region of the water at the same location all the time, so we actually do another reproducibility study that we actually run this decomposition with 11 different calibration regions for water. So it's all this yellow circles marked here. And just to remind you that I'm repeating everything for 5 different locations. So at the end, I have 55 non-Gaussian image generated for every scatter error cases, so that we can do some statistical analysis for the study. So this is the overview of the images we have. So overall, it looks quite similar. So this is reasonable because our error gap is relatively large. But the very left column is the ideal scatter correction case, and the SPR is shown below it, each of these 2 collimations. It's below 25%, so SPR is pretty small. And so from the second column, which is the no scatter correction case, if you go from second to the very right column, which is the overestimation of scatter by 20%, we're actually applying an increasing amount of scatter correction on the image, and you start to see more of a contrast between each of these inserts. And maybe when you overcorrect it, there will be more and more darker pixels show up on the water bath. And we did a quick quantitative analysis for the widest collimation case that we studied is like 15 centimeters on the detector. And so the metric we use is the signal enhancement. So because in bone marrow edema imaging, we actually care more about the change of the water of edema relative to the healthy region of the trabecular bones. So essentially, you see this on the very left corner, we have the 3 colorful inserts. So we actually compute the difference in each of these 55 images between each of these 3 insert and this BME 80, this insert on the top of the lowest edema concentration. So theoretically, you should see a signal enhancement on this plot. So this box plot actually, this box, the interquartile range actually represent the interquartile range for the all 55 cases. And overall, you can always see a good amount of signal enhancement across all these different scatter correction errors. And without scatter correction, things are a little bit worse because the spreading of the errors is pretty wide. And with more and more accurate scatter correction, I think things looks closer to this ideal scatter correction cases. And by the way, if you're wondering why this BME 100 and BM 100 bone plots actually are similar, actually this is supposed to be the same value because we keep the same water and fat ratios, only change the bones in there. So theoretically, both of these shows as pure bright signals, like same equivalent amount of signals on this non-calcium image. So just some very quick comparison for the interframe interpolation that we applied. So this is a reference image. The second column is actually we acquire a separate acquisition where we have a matched or consistent high energy and low energy repath. So use as a reference. And then the next three columns are the decompositions when we use this 0.5 mismatch rays. If we do not do any interframe interpolations, by the way, so you can see this pretty strong edge artifacts, and this colorful image down there is actually a difference between each of these three cases with the reference. So the artifacts mainly is on the edge. But when we do some simple interpolation techniques like a linear and spline, especially for spline, actually we can remove most of the edge artifacts. So this is actually pretty surprising for me. And also, by the way, the center of rotation, I think I forgot to mention, is actually for these images are actually down here. So actually the top portion of this phantom go through even a wider sinusoidal curve. But the spline interpolation can more or less recover this mismatch, this 0.5 degree of mismatch. And this another quick comparisons for our detector artifact corrections. So the reference is, of course, we apply all the lag and glare and scatter corrections. And then we turn the lag off and generate the image, and turn the glare correction off and generate another image. And overall, the effects are not that big, especially for lag. It's about only a 10 Hounsfield units enhancement on this side of this comic shape artifact. For the lag, you can see this pretty bright ring outside because you are reconstructing a relatively soft edge of the phantom. This is okay if your region of interest is closer to the central of your phantom, but in our case, the insert is more closer to the boundary of the phantom, so we actually need this correction for our studies. So to wrap up this study, actually, I want to quickly show you one or two slides about the cadaver study that we did. So it's the animal cadaver, by the way. It's adult sheep. The way we do it is, so the animal is healthy and alive at the beginning, right? So our collaborators from Colorado, they did a minimal invasive surgery on both the knees of the sheep, and to induce the bone marrow edema on the medial condyle for both of the femurs. So you can see this is the medial condyle for the left knee, and this is the medial condyle for the right knee, and both have a little bit of a diffused edema signal. This is because actually the animal and the human are different, right? So for human, normally we see more condensed edema signals, but for animals, it's relatively diffused. So this is actually a more challenging case than imaging a human. And then we use the same test bench setup, like the photo I showed you earlier, to scan both of these lags with the same protocols, and we use a 60 millimeter of axial collimations for this. Here's just a quick result. So this left block is for the left knee, and the right block is for the right knee. And so just for comparison, we're trying to look at the T2 MRI scan and this non-calcium image to see whether, so theoretically the edema signal should show brighter in both of these images. So it's actually a good comparison. And we can kind of reconstruct this edema on the medial condyle for both of these cases, you can see here. But the one issue that we're actually trying to deal with is, as you can see, there's some false positive signals on the other condyle that's supposed to not be there. Like especially for this case, like this signal on the lateral condyle is supposed to be healthy. The lamb is supposed to be there's no edema on this sheep lateral condyle. So this is a false positive signal that we are working on this. And just draw a conclusion for this. So in this study, we experimentally validate a ridge size phantom and the animal cadavers for bone marrow edema imaging using this dual energy cone beam CT and this robotic arm geometry. We show that it's feasible with relatively wide collimations up to 15 centimeters, and that's without any scatter grid. And it can detect about 20% of water content or edema signal enhancement, and is reproducible across all different object positions. Also, Just to mention it again, the error gap of this study is pretty long, so the SPR overall is small. So if you introduce 20% of the scatter error, it's actually the difference is not that big in this study. So it shows a certain amount of robustness, but we're certainly working on actually a larger phantom to see what they're going to happen with a larger SPR. And we also show that the comprehensive artifact correction framework is actually necessary for all the detectors and scatter, and even for the decomposition coefficients calibrations. And then the bonus surprise result is some simple interpolation techniques actually enough for us to interpolate our to generate this matched projection views for this 0.5 degree KV switching. So for the future work, we're, like I just mentioned earlier, we're evaluating this doing more experiments on the animal data to remove more of the false positive signals. And we also evaluate, we're also studying more challenging cases, such as a larger object and with even a shorter error gaps, such as the Extremity CBCD scanner. This scanner is actually interesting. You guys might see it in the tour tomorrow, actually. Some of my colleagues will definitely show you a different version of it. And we also plan to validate on the real Siemens multi-system RAG scanner. And the last thing we haven't really got a chance to do is to apply the model-based three-material decomposition algorithm, which has got a paper published recently. It's one step, so you can get rid of any ray mismatch. And that's it. Thank you for your attention.
I think we have time for a short question.
Thank you very much. Those are very impressive results. I'm curious if you would try to stress test this decomposition algorithm to find one case where it's really difficult, presumably because the volume preservation constraints does not hold anymore. Do you have a feeling for what that case would be? Something where you have maybe water, fat, and calcium, but not in a compressible mixture?
Yeah, that's actually a pretty good question. I think you will probably see, so volume conservation constraint, first of all, is like two parts, right? You sum to 1 plus you have is bounded between 0 and 1, like the percentage of material. So I think you will see more of the truncation effects, like some of the material will truncate to upper bound or truncate to lower bound, or yeah, we haven't really. I mean, apparently this is an issue for a pretty common issue, but we haven't. We probably have to do some experiment with that, but I cannot tell what's going to happen actually.
Thanks.
Very nice talk. A couple questions. You said that the lag impact is very negligible. Is this just for the centered position, or you also investigate for the off-centered positions?
You mean for this cadaver study?
Yeah, the one that you showed.
Okay, so for this study, actually, we cannot perfectly center it because it's
the lab phantom study. You had 5 positions. Yeah, you turned off a lag correction. You said the impact is very minimal. Yeah, somewhere here, right?
Yeah, so this axis rotation is right here actually. So this is off centered.
This one is.
Yeah, this is definitely going to be off-center because if this center of rotation is at the center, then you won't see the lag effect actually. So.
Right. So you turn off the lag, the impact is quite minimal, or?
Yeah, I think it's pretty minimal. It's about 10 or maybe a little bit more Hounsfield unit on this non-Calcium image.
Okay.
So if it's because I think it's reduced most of the artifacts. So.
Yeah, I'm just trying to reconfirm what you said, whether I understood.
Yeah, that's what I'm thinking about. I mean, we're definitely going to try some larger phantom with a more complex structure that is not like a circular insert, right? Because it depends on many things. Like, for example, you have more complex bone structures, it might be not that accurate, or you have a very poor signal. There's also, many reasons.
Thanks.
One last question.
I actually have 2 questions.
Please.
The first one is in the final results with the cadaver study that you've showed, is that with the mismatch projections, the results? Is that with the mismatch of projection?
Yeah, this is KV switching results, but we applied interpolation. So
do you have data with matched projections?
We also have the data with the match, but I haven't. I just didn't show it here actually. Sorry.
Okay, so if you do that, do you still get those false positives with matched projections?
That's a good question actually.
Because you mentioned that at the very end that you're doing that one step so that you can get rid of the mismatch.
I think for one step you can definitely get rid of the interpolation. So you can deal with the 0.5 mismatch. But for this algorithm, I think possible. I mean, it could be a reason that is caused by some of the interpolation errors.
Okay.
But we'll definitely compare with the matched decomposition and see.
Right.
I think it's
right.
because this is a pretty complex structure, so it's likely.
Cool.
Okay.
So my second question.
Maybe we can discuss.
Oh yeah, sure. Of course.
Thank you.
Okay, so that concludes the session. Let's thank all the speakers again.